We begin with section 1.1, numbers and sequences. Rational numbers are all numbers of the form p divided by q, where top and bottom are integers. Moreover, q is a non-zero integer. So number one, p and q are integers. P can be 0. Q cannot be 0. Examples of rational numbers: 1/2, -5/3. 2, by the way, 2 is a rational number. Here's why. 2 can be written as p/q. For example, 2 is equal to 2 divided by 1. Top 2 is an integer, bottom 1 is a non-zero integer, so 2 is a rational number. 0 is a rational number because 0 can be rewritten as 0 divided by 1. 0 top is an integer, 1 bottom is a non-zero integer. 50/10, and so on. Notations. By n, we denote all natural numbers, that is, positive integers, 1, 2, 3, and so on. Z, all integer numbers, 0, plus minus 1, plus minus 2, and so on. Q, our rational numbers, are all real numbers. Folks, any questions before we continue?
Oh, how come 0 isn't a natural number?
Well, it's just definition of natural numbers. By definition, we decided to exclude 0 from the set of natural numbers.
Would that stand throughout the course? Do we always assume that 0 is not a natural number?
Yes.
Okay, thank you.
Next question is, so looking at these 4 examples, it's absolutely obvious that there are integers that are not natural numbers. For example, 0. 0 is an integer, but it is not a natural number. It is absolutely obvious that there are irrational numbers that are not integers. For example, 1/2. 1/2 is a rational number, but it is not an integer. Question is, are there real numbers that are not rational numbers? Now, the question is much more complicated. In other words, is it true that there are numbers that cannot be written as integer divided by a non-zero integer? One can say, hey, square root of 2. Well, guys, but how to prove that square root of 2 cannot be written as integer divided by a non-zero integer? This is one of the goals of today's classroom meeting. We will prove the following. Square root of 2 is irrational. What is an irrational number? A number which is not rational is said to be irrational. We will prove that square root of 2 cannot be written as integer divided by a non-zero integer. Now, in this course, we will discuss 2 very different proofs of this. We begin with way number 1 of proving that square root of 2 is irrational. We will use the so-called well-ordering property. Well-ordering property says that every non-empty set of positive integers has a least element. By the way, some authors state the well-ordering property in a more general way. Please take a look at this. Every non-empty set of integers that are greater than some fixed integer has a least element. Note that what is written here immediately follows from this. However, one can show that actually both statements are equivalent. Any questions?
So are we assuming the set is finite?
No, we are assuming that the set is non-empty. It does not have to be finite. Every non-empty set of positive integers has a least element.
Okay.
Other questions here?
Is there a reason why it has to be positive integers for the well-ordering property?
Once again, some authors state the well-ordering property in this more general way, but important, both statements are equivalent. Number two, in this course, it is enough to state the well-ordering property in this way. We just don't need more general version of this property. Other questions?
Does the well-ordering property follow from the Archimedean principle?
It all depends. We can think about this as about an axiom or a provable theorem. Was that your question?
Yeah. Thank you very much.
Okay. So let us prove that square root of 2 is irrational. Let us prove that square root of 2 cannot be written as integer divided by a non-zero integer. The general approach is the following. We will prove this result by contradiction. Here's what I mean by that. First, we assume to the contrary that square root of 2 is rational. The goal after that is to get a contradiction. When we get a contradiction, this will mean that square root of 2 is irrational. Of course, hard part is to get a contradiction. So, assume to the contrary that square root of 2 is irrational. That is, square root of 2 is a divided by b, where a and b are integers. Moreover, b is not equal to 0. Here's another important thing. Without loss of generality, we can assume that a and b are positive integers. Indeed, if a and b are negative integers, multiply top and bottom by -1. As the result, both top and bottom will be positive integers. Next step. If we multiply both sides here by b, we will get a is equal to b times square root of 2. After that, let us consider the following set. The set S consists of all numbers k such that both k and k times square root of 2 are positive integers. Big question is the set S non-empty? The answer is, the set S is indeed non-empty. Because if we look at 2 and 3, there exists a positive integer b such that both b and b times square root of 2 are positive integers. Well, it's written over here. B is a positive integer. Since a is a positive integer, b times square root of 2 is a positive integer. Since both b and b times square root of 2 are positive integers, this set S contains at least one element. So S is non-empty. Guys, any questions about this portion? We just showed that this set S is non-empty. Since set S is non-empty and contains only positive integers, we can apply the well-ordering property. Let us go back to the well-ordering property. In the well-ordering property, we are talking about non-empty sets of positive integers. Indeed, S is a non-empty set of positive integers. K is a positive integer. Since S is a non-empty set of positive integers, by the well-ordering property, S has a smallest element. Let us denote this smallest element by a lowercase s. So, since S is an element from the set S, both a lowercase s and lowercase s times square root of 2 are positive integers. Guys, any questions about this portion?
So how can you make assumption number 2? Is it off the assumption that square root or that 2 is positive?
Very good question. So how can we assume that A and B are positive integers? Here's what we do. Step 1, we assume to the contrary that square root of 2 is rational. Means square root of 2 can be written as integer divided by a non-zero integer. Assume also that both top and bottom are negative. In this case, if we multiply top and bottom by -1, top and bottom will become positive. Conclusion: if square root of 2 can be written as negative divided by negative, square root of 2 can be written as positive divided by positive. So without loss of generality, we can assume that square root of 2 is positive divided by positive. Did I answer a question?
What about negative divided by positive?
Very good question. Cannot be. If top is negative, bottom is positive, A divided by B is negative, but square root of 2 is positive. Cannot be.
Is there a premise somewhere that says that?
Well, we know that the value of square root of 2 is approximately 1.4, which is positive.
I'm just going to run with the fact that we can use a calculator to determine the value of square root 2 and other values.
Excellent question. So, how can we know the value why square root of 2 is positive? Simply by definition. Square root of 2 means positive number, square of which is 2. Other questions, guys?
I am a little confused how A and B can't both be negative.
So see, if we assume that square root of 2 is rational, indeed, square root of 2 can be written as negative divided by negative. If this is the case, just multiply top and bottom by -1. The top and bottom become positive. Therefore, let us for convenience assume that top and bottom are positive from the very beginning. Guys, any other questions?
So I have a question.
Yes.
So just to be clear, I know you talked about this, but just to make sure I understand correctly,
Mhm.
whenever we consider a square root, we're only considering the positive square roots.
Well, it's not like we are okay. Please take a look at the graph. This is the graph of square root of x.
Okay.
Note that there is nothing here. The range of square root of x is all non-negative numbers. Moreover, square root of x is equal to 0 only if x is equal to 0. Conclusion, if x is equal to 2, square root of 2 is positive. Did I answer the question?
Yes.
So, let me repeat once again. Assuming to the contrary that square root of 2 is rational, we come up with the following. If square root of 2 is irrational, there exists a positive integer b such that b times square root of 2 is also positive integer. Since both b and b times square root of 2 are positive integers, this set S is non-empty. Since set S consists of positive integers, and since S is non-empty, we can apply the well-ordering property. By the well-ordering property, S has the smallest element. Let us denote the smallest element of S by a lowercase s. Note that since S is an element of our set, both a lowercase s and lowercase s times square root of 2 are positive integers. Here is what we do next. Let us consider a new number, W. W is S times square root of 2 minus S. The goal is to show that W is again from the set S, and W is smaller than S. Obviously, this will give us a contradiction because we assume that a lowercase s is the smallest element from S. If we show that W is from S again and smaller than a lowercase s, we will get a contradiction. So, how do we show that W is from S and W is smaller than a lowercase s? First, let us show that W is from S. Here's how we do. First, let us show that W is an integer. Why W is an integer? Well, look at 4. Note that according to 4, S is a positive integer. S times square root of 2 is a positive integer. So both S and S times square root of 2 are integers. Note that integer minus integer is an integer. Conclusion: W is an integer. Moreover, W is a positive integer. Indeed, if we factor out S, we get this. S, according to 4, is a positive integer. Square root of 2 minus 1 is a positive number. Positive times positive is positive. Therefore, W is positive. So, W is a positive integer. Guys, any questions about this portion?
So does square root of 2 minus 1 greater than 0 come from the calculation?
So, since the function is increasing, and since square root of 1 is 1, square root of 2 is greater than 1. Therefore, square root of 2 minus 1 is positive. Did I answer your question?
Yeah, thank you.
So, in I, we proved that W is a positive integer. In II, we prove that W times square root of 2 is a positive integer. Well, first of all, it is obviously positive because by I, W is positive. Square root of 2 is positive by this, and we know that positive times positive is positive. Question is, why W times square root of 2 is an integer? Here's how we prove. Note that W times square root of 2 can be rewritten as this because, according to what is written here, W can be replaced by S times square root of 2 minus S. After that, let us expand parentheses. S times square root of 2 times square root of 2 is 2S. S times square root of 2 is S square root of 2. And now note that since 2 is an integer and S is an integer, 2S is an integer. Also, by 4, S times square root of 2 is an integer. Integer minus integer is an integer. So, W times square root of 2 is positive. W times square root of 2 is an integer. Conclusion, W times square root of 2 is a positive integer. Lastly, in 3, we show that W is lesser than S. Here's why. According to what is written here, W is S square root of 2 minus S. Factor out S. Since square root of 2 minus 1 is lesser than 1, S times square root of 2 minus 1 is lesser than S. And now let us put pieces together. By 1 and 2, W is an element of S because both W and W times square root of 2 are positive integers. By 3, W is smaller than S. Repeat once again. W is from S and W is smaller than a lowercase s. We got a contradiction because s is the smallest integer from s. Since we got a contradiction, square root of 2 is irrational. Please ask me questions.
Yeah, so I know of the other less rigorous proof that you prove that A is a multiple of B, and assume that A is not a multiple of B, and that hence you get a contradiction that way. Is that not rigorous enough for this course?
We will discuss this proof later in this course.
Okay, thank you so much.
Yes. Other questions?
So if we were to choose a rational number instead of square root of 2, what would go differently?
Yes. In other words, suppose instead of square root of 2, we have, say, 1/2. We apply same approach. Will we be able to prove that 1/2 is irrational? No. Let us try.
Okay.
Let us replace square root of 2 by, say, 1/2. Or say, for simplicity, let me replace square root of 2 by 2. All right? So here 2, here 2, here 2, and therefore here 2. And therefore here 2. So we now consider the following set. K such that K and K times 2 are positive integers. So far, everything is good, correct? Sentence number 1 is fine. Note that set S is non-empty since both B and 2 times B are positive integers. Therefore, as before, we can apply the well-ordering property. So this set S has a smallest element, which we can denote by lowercase s. And then 4 is fine. S and 2 times s are positive integers. This portion is also fine. Let us consider W, which is equal to 2s minus s. Correct? Here is one problem. 3 will fail. We will not be able to prove that W is lesser than s because 2 times s minus s is s, which is not lesser than s. Does this make sense?
Yes.
Now, you can say, hey, what if instead of square root of 2 we have, say, 1/2? Yes, if instead of square root of 2 we have 1/2, then W is s times 1/2 minus s. In this case, 3 is fine, but this portion is not fine because W will not be positive integer because 1/2 minus 1 is negative. You see it?
Yes.
By the way, we will discuss it tomorrow. I'll show you what happens if we replace square root of 2 by, say, square root of 3, or square root of 5, or cubic root of 2, and so on.
Okay. That makes sense. Thank you.
Yes. Other questions?
By the definition of we'll actually go a little bit down, I'm sorry. Where the number that is not a number that is not rational is said to be irrational.
Yes.
So essentially, if I'm understanding correctly, that would mean that the number that is not in the rational set is irrational.
So despite the fact the definition of irrational numbers is written, it does not necessarily mean that irrational numbers exist. This has to be proven. And this is exactly what we prove in this example. One of the most important things about example number 1 is the following. Irrational numbers exist. And here is one out of actually infinitely many examples.
Okay, I think I understand. Thank you.
Other questions?
Can this proof be generalized to square root of n, where n is, oh wait, sorry, never mind, that wouldn't work.
No. Look, you asked a very good question. How to generalize this result? We can generalize this result in many different ways. For example, tomorrow we will show that square root of 3 is irrational, square root of 5 is irrational, and so on. Now, in section 3.5, let me take a look at 3.5. We will prove a much more general result. Here it is. Suppose alpha is a root of this polynomial, where the leading coefficient is 1, all other coefficients are integers. Then there are only two possibilities. Either alpha is an integer or irrational number.
Okay.
So this is a very powerful generalization. For example, if we have this in hands, it's really easy to show that square root of 2 is irrational. Note that square root of 2 is a root of the following polynomial. Over here, x squared minus 2. X squared minus 2 is a polynomial of this form. Since square root of 2 is not an integer, by theorem 7, it is irrational. Note that we can apply this approach to tons of other numbers. Take a look at this example. Let a be a positive integer, which is not mth power of an integer, which means mth root of a is not an integer. Therefore, mth root of a is irrational by theorem 7. But we will discuss it later. Was that a question?
Yeah, pretty much. So that theorem 7, we'll go through the proof of that?
Oh, of course. But in order to prove theorem 7, we need lots of tools that will be discussed later. The greatest advantage of the proof that we just discussed, we need only the well-ordering property and college algebra, pre-calculus. That's it. This is all we need. However, in order to prove theorem 7, we'll need lots of other tools that will be discussed only later in this course.
Okay.